few years into the work, we decided that we wanted to put out some white papers that described in a little bit more detail how the design worked. Because we had, filed some patents already, we had gotten some key aspects of our intellectual property locked down, and, we wanted to get more information out there for the public to read. I wish we had, not focused so much on locking down our intellectual property and had instead put more of our information out there into the open much earlier, because one person, after reading our white papers, pointed out an absolutely fundamental mistake that we had made in our calculations.
Hello, and welcome to My Nuclear Life. I'm Shelly Lesher. In today's podcast, we're going to look at the future of nuclear energy with Dr. Leslie Dewan. Leslie earned her PhD in nuclear engineering from MIT and currently runs a company investing in new nuclear energy technology. According to the Nuclear Energy Institute, in 2019, nuclear power made up 20% of U.S. electricity production and over 54% of U.S. carbon-free electricity usage. However, only 2 new nuclear plants are under construction. The first of these plants will open in 2021 and will mark the first plant built in more than 30 years. There are more large commercial facilities in various stages of permits and licensures, which can take decades of approvals. The reasons for this lag in construction will be explored in a future episode. But today we ask, is there another way forward in the field to help decrease our carbon footprint in a time when the world is desperately trying to prevent a climate disaster? The answer may lie in Generation 4 reactors, which focus not only on reducing costs, but improving safety and sustainability. Small modular reactors, or microreactors, are included in this category, which will have the advantage of offering flexibility in location and a much shorter construction time than traditional reactor designs. Today's guest, Dr. Leslie Dewan, is co-founder of Transatomic Power, one of the first startup companies attempting to bring a Generation 4 reactor to market. Leslie is a visionary in the field of nuclear energy, and this understanding has allowed her new company, Criticality Capital, to invest money in the sectors which need it the most. When fission was discovered in 1938, there were 2 possibilities envisioned for the massive energy released, resulting from the splitting of the atom. Would a reactor be built to harness the energy into electricity, or would it be focused into a destructive force? Today, Leslie and I spoke about how we can work on improving the way we harness nuclear energy and what she sees as the path forward. To start, I asked Leslie what attracted her to nuclear engineering.
It actually goes back to high school because I had 2 fantastic physics teachers in high school. Both were women, both went to MIT. One was actually the first woman to get a nuclear physics PhD from MIT back in the 1950s. And from the moment I met them, I just wanted to be exactly like them. So I ended up going to MIT just like they did, studying physics. And after I started taking my first few physics courses, I just got so excited about what you could physically do with it and what you could make with it. And at the same time, I've always been an environmentalist and, have wanted to figure out ways to move the world away from fossil fuels. And so the 2 of them came together in a really logical way. The physics and the environmentalism eventually led to nuclear engineering.
You had 2 women as physics teachers in high school?
Yeah, it was absolutely, absolutely amazing. I went to this teeny tiny girls' school in Boston, and they managed to attract the absolute best teachers. I'm still in touch with some of them.
I was going to ask, what do those high school teachers, do you still talk to them? What did they say when you went to MIT and then you went on to get a PhD in nuclear engineering? Was this normal for their students?
So I was lucky. We had an unusually amazing class. So there were just 50 of us in the class, just about. And, a few of us went on to get PhDs, a lot of MDs as well. Our high school reunions are actually the most amazing things in the world because we get back and it's just we have turned into this group of wonderful, successful, interesting women. It's really lovely.
I know that you started a company called Transatomic. And when I think of nuclear power, I think of government-backed loans. I think of large gas and electric companies that, charge for the electricity that they produce. Or I think of a research lab that is kind of working on experimental reactor designs. But your story is different. So could you tell me how transatomic power started?
So I started Transatomic in grad school with a classmate of mine. And, both of us are environmentalists. Both of us love nuclear power. And we wanted to figure out a way to basically solve some of the existing issues with nuclear reactors, some of the problems with conventional designs that were holding them back from broader adoption, the issues with safety and waste and proliferation and cost. And one of the things we were especially excited about were some of the older, nearly abandoned designs from the very, very early days of the nuclear industry back in the 1950s and 60s. Back then, there was this amazing sense of blue sky thinking around the technology. And, they came up with designs that would leave behind less nuclear waste, that were much safer, that were proliferation resistant. A lot of them, though, were very, very expensive. And they were abandoned in favor of, the cheaper and still relatively stable and secure conventional nuclear reactors. And so my co-founder and I thought, what if we can bring one of those designs back? What if we can take like the inherently good bones of one of these earlier designs and improve it with modern materials or modern computational simulations and make it into something that can be commercialized more broadly?
So how did you decide which one of these old designs to bring back? Like, how many did you look at before deciding on the one that you did?
So we actually went about it in a very, very systematic way.
Okay.
We ended up making a chart, and on the horizontal axis, so we said, all right, here are the 6 broad categories of advanced reactors that exist, molten salt reactors, metal cooled fast reactors, gas cooled reactors, all of those. And then we evaluated them on 3 key criteria. One was that the systems have high fuel utilization. So, like, basically, you're getting better mileage for a given amount of uranium, and therefore it leaves behind a smaller relative amount of nuclear waste. And then we also wanted the systems to be able to operate at pretty close to atmospheric pressure as compared to the 100 or so times atmospheric pressure that a conventional reactor operates at. That means if it's at atmospheric pressure, it doesn't have this large potential driving force that could push radioactive material out beyond the site boundary. And then lastly, we thought it would be beneficial for the system to have what's called thermal energy neutrons, which is lower energy than the fast spectrum of some reactor designs. And so this means that you're damaging your materials less, components can last longer, and overall it can have a lower cost because you're not replacing components as frequently. And once we laid them all out on those 3 criteria, the molten salt reactor design leapt out to us. It has low pressure, atmospheric pressure operation, the potential for very high fuel utilization, and you can build ones that operate in a thermal neutron spectrum as well. And then the fantastic thing about this is that there was already an existence proof for molten salt reactors. Back at the Oak Ridge National Lab in the 50s and 60s, they built one and they tested it and they operated it for several years. So we knew that at least one flavor of the molten salt reactor was viable. So that was our starting point.
So you had this table. How did you decide what properties to put on there as comparison to the conventional reactors that we use now? Why were those items important?
Those were ones that were best at addressing the waste piece, because that ties into fuel utilization, and then
Okay.
cost in terms of thermal spectrum versus fast spectrum, and then safety with atmospheric pressure versus much higher than atmospheric pressure. So we felt those were the best metrics to capture those 3 pieces there.
So once you had the molten salt reactor kind of figured out, what was the next step?
From that starting point, we wanted to figure out whether there were any ways that we could improve it. So that basically came down to changing out some of the different types of materials from what they were in the original design, and then further optimizing the geometry of the system with better types of computational simulations. And the first thing that we looked at for this was figuring out a different type of moderator material. So in the original molten salt reactor, they used graphite as a moderator. So you're slowing down the neutrons by colliding them with the carbon in graphite. That worked for their system, but you needed about 90% of your reactor core to be graphite. So you only had about 10% left of the space to be the salt. In a molten salt reactor, it uses liquid fuel rather than solid fuel, and the uranium is basically dissolved into this liquid salt. The other material change that we made was to the particular type of salt in the molten salt reactor. So the earliest versions used a lithium fluoride, beryllium fluoride, uranium fluoride salt, which would only allow you to dissolve in about 1 molar percent uranium. And then the other issue with that is beryllium can be very, very toxic as well. So there were some handling considerations with that. We were able to swap over the salt to just a lithium fluoride, uranium fluoride salt that lets you dissolve in about 23 molar percent uranium fluoride. So about 23 times as much uranium in the salt. And then with the moderator that we changed, we were able to go from about 10% of salt in the core to about 50% salt in the core.
Does that address the fuel efficiency then, if you're able to incorporate more uranium into the salt?
That actually didn't directly get into the fuel efficiency, but it got into the amount of enrichment that you need. So in the original molten salt reactor, in the prototypes, they enriched the fuel to about 90% uranium-235, and at a minimum required about 30% uranium-235, which is too high an enrichment for anything beyond a national lab experiment. Whereas with our design, with much more salt in the core, much more uranium dissolved in the salt, we were able to get it down to needing just 5% uranium-235 enrichment, which is the standard enrichment required for most fuel.
Oh, that's great. So then that addresses the proliferation part as well.
Yes, that addresses a lot of the proliferation part. There's a bit of a nuance actually on the proliferation side with molten salt reactors where you can make the argument, and this might be a bit too much of a tangent, but you can say that in a solid fueled reactor, the fact that the fuel is in solid form and that it's held together within metal cladding, bundled together in fuel assemblies, that physical solid structure provides a barrier to proliferation. Whereas if the salt is already in liquid form, some people can argue that, oh, that makes it easier potentially to separate out uranium or plutonium from the salt because it's already a liquid. It's a bit of a nuance, but it gets at a more fundamental piece, I believe, which is that if in the future you want to build these types of advanced reactors or molten salt reactors out in other parts of the world, you're going to need to figure out new types of anti-proliferation measures and new methods of materials management and figuring out ways to make sure people don't surreptitiously remove nuclear materials from the site.
So there's a lot more to think about than just how to incorporate the uranium into the salt.
Very much so. And I think that's one of the interesting and perhaps neglected at this point pieces of advanced reactor design that everyone is going to have to think about more going forward, figuring out very concretely how to make these advanced reactors more proliferation resistant.
So if I did the math right, you were working on this before you actually received your PhD.
That's right. I finished my PhD in 2013, but my co-founder and I incorporated the company back in 2011. So for a number of years, I was working on both of them simultaneously, which made for a very, very interesting time.
So this wasn't your PhD research.
No, it wasn't. My PhD research was similar in some respects. So I was doing different types of molecular dynamics simulations, other types of computational simulations of some types of molten salt fuels, and then also simulating some types of glassified nuclear waste and seeing how those degraded over time, which is, adjacent in some ways to some aspects of this molten salt reactor design, but it wasn't directly aligned. I basically just didn't sleep for a few years.
Yeah, I can imagine. So, I mean, what possessed you to do this at a time when you were at MIT, you were working on your PhD, and you're starting this, startup company, right? So why?
Well, it was because it seemed like such an interesting problem to solve that once my co-founder and I started discussing it, we just couldn't let the idea go. We realized that we needed to pursue this, and we were pretty well positioned to dig into it. And the timing might not have been ideal, but it worked well enough.
Were you one of the first Gen 4 reactor startup companies?
We were. When we started our company back in 2011, there were, I think, maybe 3 or 4 other advanced reactor design startups out there, but we were one of the early ones. It made for some interesting times as we were, initially trying to raise funding for the design, or even just explaining to other people, both within our academic department and more broadly, what we were doing, because there was very little precedent for it at that point.
Do you think you went into it a little naively thinking about, how you were going to raise funds or how, you were going to lead this company?
Oh, very much so. There was some breathtaking naivete going on in the early days. It ended up in many ways being far, far more difficult than I ever thought that it could have been, especially because my background up until that point was just in science and engineering. I was purely in academia. So I didn't know very much at all about how difficult it was to start a company, especially one in a very regulatory heavy space.
So how did you find funding?
So after we put together an initial business plan and kind of figured out what a market could potentially look like, figured out what the key experiments were that we wanted to run, and sort of what our process would look like from that point, we started having conversations with different potential investors in our company. And the first few conversations were very, very interesting because the people that we talked to, they were really only familiar with making software style investments, ones that would have a very quick turnaround. So we'd pitch them on our technology, and, some of them would be very interested in it. They could see the potential, and they said, "Oh, that's wonderful. We want to invest. Can you have one built in 18 months?" And we just had to say no. Like, there is no way whatsoever that could happen. Like, it will take, it'd take about 10 years. There's a lot of technology still to be developed. There's a regulatory process to work through. There's some legislative pieces that need to come into play as well. And it actually wasn't until we started having conversations with people who had previously made investments in aerospace that we started finding people who kind of understood what this type of undertaking would involve. Our main early investor, who actually invested in all of our rounds, was Peter Thiel's Founders Fund, who made one of the first investments in Elon Musk's SpaceX. And they understood the timelines and the dollar amounts involved in investing in nuclear because they were so similar to aerospace. So when we told them our numbers, they said, "Okay, well, that's about how long it took and how much it cost to get the Falcon 9 off the ground. So we understand it."
Oh, that must have been refreshing to hear that someone actually understood the timetable that you were looking at.
It was really excellent when we had our first conversation with them. And what especially helped is that they had a chief scientist who had a PhD in nuclear physics. And so he understood the science behind it as well, which made for some fantastic, more in-depth conversations.
You mentioned the government regulations. How did that piece play into the company and what you were able to do?
So the government regulations around nuclear are quite strict, and I think that's very good, actually. I think if any area needs to have tight government regulations, it's around the design and operation of nuclear power reactors.
Yes.
Though one of the issues for many years, and continuing to this day to some degree, is that the regulations as currently written by the US Nuclear Regulatory Commission basically only apply to conventional nuclear reactors. They say things like, your containment dome needs to be this many feet thick of steel and concrete, for example, like very specific and very geared towards conventional nuclear reactors. And it wasn't until quite recently that the Nuclear Regulatory Commission has started to write regulations that are applicable for advanced reactors as well. And so now, like, after many, many, many years, advanced reactors are finally starting to get a pathway towards regulation and licensing, whereas before that just didn't exist at all.
What was it like when you started to receive kind of all the public publicity and accolades, like being named Times Magazine 30 People Under 30 Changing the World or National Geographic's Emerging Explorers?
It actually just made me really nervous for the most part. Like I of course felt very honored, and I was very glad that they thought of me for these awards, but part of me just wanted to stay a bit lower key. Like it felt premature to me in a lot of ways. And I figured it would be good for the company overall to take these opportunities.
Did it bring some unwanted attention, though, as well?
It definitely did. And what was kind of tricky for me is that it brought on a lot of criticism, but I could kind of see the point to a lot of criticism. Like people were saying like, well, they haven't built one yet. And I said, well, yes, that's true. Like we have what I believe is a solid plan for building it. We have a solid set of experiments that are lined up, but it's still going to be a long way to go before we can validate all of the aspects of the technology, work our way through the regulatory system. Like we have a really good idea of where this is going to go, but it's definitely not there yet.
What happened next?
So a few years into the work, we decided that we wanted to put out some white papers that described in a little bit more detail how the design worked, because we had, filed some patents already. We had gotten some key aspects of our intellectual property locked down, and, we wanted to get more information out there for the public to read.
And did that result in any feedback?
Yes, and some of it was very, very, very important feedback, and it's what made me realize that I wish we had, not focused so much on locking down our intellectual property and had instead put more of our information out there into the open much earlier. Because one person, after reading our white papers, pointed out an absolutely fundamental mistake that we had made in our calculations. It was a heart-stopping moment. And we took their feedback, reran our calculations, and realized that we had, in fact, really fundamentally miscalculated an aspect of our reactor design. In our initial version, we thought that it would be able to maintain criticality running solely on spent nuclear fuel. But it turns out that that wasn't possible with our design. It would need a minimum of 5% enriched uranium.
As a scientist, I need to ask, how many times did you run that calculation?
Oh gosh, over and over and over again. But really, once we figured out the mistake that we made specifically in the code, it was clear that we were wrong. It just came down to exactly how wrong were we? Like, is there any way of recovering, what we initially thought that we'd be able to do? And partly, it turns out that the design still had the same safety benefits, still the same low cost compared to other types of reactor designs, but it lost the ability that I initially thought it would have to consume spent nuclear fuel. And, that was really the problem that I really, really wanted to solve. I felt like that was just an absolute key piece for a new type of reactor design. And with that lost, it was really tough.
So what was the next step?
This is where my team at the company was so amazing, because as I was dealing with the fact that my heart was no longer beating, my team just said, okay, well, this is a new challenge. We're going to solve it as best we can, given the new constraints that we now know about. We're going to figure out what the new design looks like. And at the same time, we're going to pour through all the rest of our code and make sure there aren't any other mistakes that have been lurking in there. And then as part of this as well, we decided to put out more information, like not just additional white papers. We put out an in-depth white paper on the neutronics of our reactor design, because it was the neutronics specifically that had the big mistake. But, we also put out more details of how particular parts of our code worked, different dimensions of our reactor, because we realized now was the time to get more information out there in the public domain.
Is all the information now out in the public domain from Transatomic?
Just about all of it is. So basically what happened next was we came up with a new design for the reactor that was not able to consume spent nuclear fuel, but it still had some good benefits. It was able to get about twice the fuel utilization compared to conventional nuclear reactors. It had good safety benefits, good proliferation resistance compared to other types of designs. And we persisted for about another year and a half, trying to commercialize that newer version of the design. But because of all of the time that we lost in redesigning it and some of the existing regulatory hurdles, we realized that we weren't going to be first to market. We weren't going to be second to market. We weren't going to be third to market. And it just seemed unethical at that point to continue taking investor money to commercialize a design that just wasn't going to do what I felt it ought to do. And so what we ended up doing at that point, I made a particularly terrifying series of phone calls, called up all of my investors, told them that I didn't see a path forward on the business side anymore. And I asked for their blessing to put all of our information out into the public domain. So we ended up relinquishing all of the patents that we had. We ended up putting together more of our design documentation, more of our blueprints, and actually in conversation with the Department of Energy, because it's necessary to bring them into the loop and in all of this, we ended up putting our design out onto GitHub, where it remains in the public domain to this day. And it's a bittersweet resolution because, of course, we weren't able to commercialize it the way we initially wanted to. We didn't succeed in this initial vision that we had, but parts of it are still being used, which is nice. In some types of experiments within academia, people are using our blueprints and code for some of their analyses. In some projects within ARPA-E, within the US Department of Energy, they're using aspects of our design. And the technology lives on in some way.
It's good that it lives on. It's hard to believe that this is an easy problem to solve when it comes to advanced reactor designs.
That's true. I remain very optimistic that other companies will be able to solve this problem of designing reactors that can consume spent nuclear fuel while remaining economical and proliferation resistant and safe. Like, that's achievable, though tricky. And even though we weren't able to do it, I think that a solution is certainly out there.
What do you think it'll take for the big electric companies to adopt a new design?
For that, I think it'll just come down to cost. I mean, that's the first order piece that you'll have to look at. If you can make advanced reactors that are cheaper than fossil fuels, or at least cheaper than coal, then I think you'll see a pretty decent market for those. And there are a few different market segments that you can look at. So it'll be tricky, I think, in the near term for an advanced reactor to be cheaper than natural gas at the grid scale, because natural gas is just very, very, very cheap, especially now. But if you look at, for example, very small scale power needs, areas of northern Alaska and Canada that right now they're off the grid, they get their power from trucked in diesel fuel that powers diesel generators. That's very, very, very expensive. And so you could imagine small scale nuclear reactors that would be cheaper than that trucked in diesel fuel. So that could be a good area where advanced nuclear could get a toehold in the market.
So with people thinking about renewables, they're thinking about kind of more smaller scale energy. So is this where you think that these smaller scale nuclear reactors kind of are finding this place?
That's what I'm imagining. So I think microreactors could be one area, or similarly, small modular reactors that would be, say, producing between 50 and 250 megawatts electric. Those could be useful for powering data centers, for example, in the future. I see the world trending away from these sort of gigawatt scale large nuclear power plants because the electric grid in general is becoming so much more distributed. You see much more of a need in the market for these very small to medium scale reactors.
So, what have you been doing since Transatomic?
So, right now, I'm still committed to nuclear, and I still very firmly believe that people will be able to develop better types of advanced nuclear reactors that can solve the problems that are holding back the current designs and figure out reactors that can work well alongside solar and wind and hydro and geothermal. So what I'm doing right now actually is doing some investing, putting together an investment fund in new types of nuclear technology, other types of carbon-free energy production, some other types of sustainable building materials like carbon trapping concrete, figuring out some new technologies that can address the gaps that I believe will emerge in the nuclear supply chain in the coming years. And so, what I want to do right now is basically figure out ways, using this investment fund to build up the nuclear ecosystem as a whole, because I think there's still so much potential there.
That's very different than where you started, right? Because you started saying, I'm a scientist and all I've done is science and had no idea about how to run a business. And now you're actually running a capital fund.
Yes. So it's been a really, really interesting transition for me. I mean, one of the things I found that I really enjoyed as I was putting together my company was that I really liked both the business aspect of it and, also kind of thinking about the supply chain pieces of nuclear, about how, you can develop really, really good technology for a reactor, but if you can't get the materials that you need on time and at the necessary scale, then you aren't going to be able to build up the reactors quickly enough to actually make a difference when it comes to greenhouse gas emission. And so I think now I have enough experience that I'm able to look at the sector as a whole and figure out ways to help accelerate its development.
Where are some of these gaps in the supply chain?
So I think one of the gaps is in terms of some of the advanced materials that some of the reactors require. Some of them need some very exotic, high temperature steel alloys that we can make, and we can make them at an industrial scale, but we wouldn't necessarily have enough capacity within the United States to build multiple advanced reactor units out of these materials. So that's one of the areas. Another tangentially related piece is just the labor force necessary for building advanced nuclear reactors. Right now, there aren't very many nuclear reactors under construction in the US, and there haven't been for about 40 years now. And so we're sort of at the national level losing that expertise in how to make them. And so I want there to be, more coordination with labor groups, with the AFL-CIO on training people and looking at this as a future jobs opportunity for making these reactors.
When you say the labor force, you're not just talking about then nuclear engineers, you're talking about all of the auxiliary staff as well.
Exactly. Yes, auxiliary staffing for the site, and I think even more importantly, the construction workers who are capable of and certified in doing nuclear grade construction, just ones who are able to, handle the rebar and pouring nuclear grade concrete, things like that. Doing X-ray testing of components after the fact to make sure that they're up to par.
Wow, that's something I hadn't thought of because there's a lot of push now to try to get students to go into nuclear engineering, into nuclear science, but I never even thought about that other aspect of it.
Yeah, it's a crazy piece because it's absolutely necessary, but at the same time, it's neglected by just about every advanced reactor designer that I've talked to because it's not a near-term problem. It's a problem that'll only become apparent, maybe 5 or 10 years out into the future.
Well, and by that time, it may be too late.
Exactly, because it takes time to train people to be able to do this.
Wow. So, what advice do you have for young people who want to go into the nuclear industry?
I think my advice would be to think big. Nuclear inherently happens at scale. You can do some immensely good things with it. So, don't be limited by your preconceptions of the industry. There's a lot of potential out there.
And I have one more question for you. Where do you see you in 10 years?
That is an excellent question. I'm not sure. I love the investing that I'm doing now is just absolutely fascinating to me. And at the same time, I still want to build things and make things. I'd like to find a way to bring a nuclear reactor that can run on nuclear waste to market. That's maybe my white whale.
I was going to ask if that's still the dream.
That is still the dream. And I hope to one day make that a reality.
Thank you for listening to this episode of My Nuclear Life. If you have a comment or an episode idea or just want to send us an email, our address is mynuclearlife@protonmail.com. I would like to extend a special thanks to our guest, Dr. Leslie Dewan, for taking time out of her busy schedule to talk with me today. And also thank you to Lexi Weghorn for her help with this podcast. Please join us next time when I'll speak to an expert about another way nuclear science impacts your life and the world around you.